Alrighty. In my very humble opinion, one of the best lines of evidence that the Earth is a globe is the existence of flights in the Southern Hemisphere. And the main one we're going to look at in the video today is the flight from Sydney, Australia, across to Santiago in Chile. So on this slide, we've got two paths. The green path is the globe Great Circle route. And as you can see, after it takes off from Sydney, it heads southeast towards New Zealand and actually passes south of the South Island. And it keeps heading southeast until it gets to almost 62 degrees south latitude. And then it starts heading northeast up towards Santiago. The yellow line, however, is the shortest path that the plane would take if the Earth reflected the azimuthal equidistant map. Or some of you like to call it the Gleason map. So on a globe, that yellow line looks like an enormous detour. But as you'll see in a second, that yellow line, if plotted on the AE map, is actually a straight line. But for now, just have a look at how different this route is. So for starters, it heads north-northeast and would actually go over Brisbane in Queensland, through the Solomon Islands, gets to almost 46 degrees north latitude, so way north of Hawaii, and then comes through the continental United States, through Oregon, Utah, Texas, through Central America, and along the west coast of South America until it gets to Santiago. And here are those two routes again, but mapped onto the dirt pizza. So again, the Great Circle route goes south of New Zealand, gets to about 62 degrees south, and then heads northeast up to Santiago. And that yellow route, which looked really silly on the globe, is actually a straight line on the AE map. So over Brisbane, through the Solomon Islands, over the USA, and down to Santiago. And the reverse is also true. The Great Circle route, which is the shortest route on a sphere, looks like an enormous detour when you map it out on the AE map. So, which route does the plane actually take in reality? Well, according to flight tracking websites like Flight Radar 24, they follow the Great Circle route. So here's a recent flight from Qantas, QF27, that heads south of New Zealand and then northeast up to Santiago. Now, the first claim from the flurfs is that this flight just doesn't exist. And one of the reasons I know that this flight exists is because I actually have a friend who is cabin crew for Qantas, and she's on this flight a couple of times every month. Obviously, not everyone has cabin crew friends, so failing that, there is a live stream channel on YouTube called SydSquad, and they broadcast from Sydney Airport. And it didn't take long to find one where they show the plane actually taking off. So claiming the flight doesn't exist is pretty silly. So, given the flight obviously exists, the second claim that the flurfs make is that the data on those flight tracking websites is fake. And the number one reason to believe the data isn't fake is because you can collect that data for yourself. All you need is one of these cool little USB dongles, which are only about $50 US. And here's mine in action, and we'll only look at about 30 seconds or so, but as you can see, the planes actually broadcast their position every few seconds. Now this data is with the antenna inside my house, literally sitting on top of my computer, and I'm in the suburbs surrounded by other houses and terrain. Obviously, if you take it outside, up on a cliff near the ocean somewhere, you'll get a much better signal, and can usually track planes up to about 500 kilometers away. So if I know my position and I get a message from the plane giving me its coordinates, I should be able to work out exactly where to look in the sky. And you can use that data to double check that the plane is actually where it says it is. And the Flight Radar 24 app actually has a really cool augmented reality feature that uses your position and the direction you're pointing your phone in to overlay little pointers to all the planes nearby. So here I am tracking QF19 leaving Sydney for the Philippines, and the app does a reasonable job of telling you roughly where you should be looking, and lo and behold, there it is. But typically after about 50 kilometers or so, you can't really make out the planes anymore. So we're back to listening to the signals. And there are 3 points along the Great Circle route where you can listen to the plane's position once it leaves Sydney. So you can track it to the southeast. Someone in Queenstown, New Zealand could track it going south of them. And then someone on the coast of Chile could track it coming up from the south along the coast. So I don't really know what the FLIRF response is to this. Maybe they'll say that once it's out of range of land, it tries to get back onto the AE route. If you want to claim that, then I guess all the pilots have to be in on the conspiracy as well. Obviously, the best way to make sure this data isn't fake is to actually board the flight yourself and bring a GPS logger with you. So here is some data from a flight that I took to Los Angeles a few years ago. The green line is the outbound leg from Sydney to LA, and the red line is the return leg. We don't usually come back north of Hawaii. Most of the time it's south of Hawaii both ways. And taking this flight from Sydney to Santiago is certainly a lot cheaper than a trip to Antarctica this December. So, surely the FLIRF community can put together $2,000. Or if you're extreme tight asses, maybe hang out in the boarding lounge and just beg someone who has a window seat if they're willing to use their phone's GPS to log the trip. So yeah, if you're going to claim the tracking data is false, you're going to need some pretty strong evidence. The second big issue you run into with this flight is the distance involved. So on the left of this screen are 4 routes and their corresponding distances. And on the right is the code I wrote to calculate those distances. I'll leave a link to my GitHub account in the description if you want to have a look at the code. The globe route is 6,135 nautical miles. And that's basically what you would get if you opened up Google Earth and drew a straight line between the two cities. So this is the route that goes south of New Zealand and comes up from the southwest into Santiago. The AE route, 13,856 nautical miles, is the straight line between Sydney and Santiago, but drawn on the AE map. So remember, this route goes way into the Northern Hemisphere, crosses the continental United States, and heads southeast into Santiago. And if you're wondering how I got that distance, I basically assume that every degree of latitude you move back from the North Pole is 60 nautical miles. If you have some other scale that you think applies to the map, then feel free to visit the GitHub link and mess around with the code as much as you like. The third box there is the globe route, but transformed onto the AE map. So if you remember back to the start of the video, there's that big semicircular route that goes around the perimeter of the AE map. And that one is 21,294 nautical miles. And finally, the fourth one is the AE route, but transformed onto the globe. So if you took that straight line path that went over the USA and traced it out on Google Earth, then it would come to 12,710 nautical miles. And these numbers are a huge problem for flat Earth for what should be a pretty obvious reason. And that reason is that the longest range commercial aircraft currently in service is the Airbus A350, and its maximum range is only 9,700 nautical miles. The A380 has a range of 8,000 nautical miles, and the 787-9 that typically flies this route between Sydney and Santiago for Qantas has an even lower range of only 7,635 nautical miles. So the big question FLIRFs have to answer is, what route does the plane take in reality, and how does it get there in only 12 hours? And without fail, that answer is Jetstreams. Yep, I'm sure all the FLIRFs watching this video up to this point have been going, duh, they catch the Jetstreams, you idiot. Yes, I am well aware that planes catch the Jetstreams. So let's see if Jetstreams can save the day, shall we? Should I put a spoiler alert in here? Yeah, no. I'll leave you guys sitting on the edge of your seats. All right, what I'll usually be given by the FLIRFs is a link to a paper from 1962, which talks about the four main jet streams. So the first one is the mid-latitude jet stream between 35 and 60 degrees latitude. And according to this paper, reaches a speed occasionally above 200 knots and has a mean height of 35,000 feet. Number two is the subtropical jet stream between 25 and 35 degrees latitude, where the core speed occasionally approaches 300 knots and has a mean height between 40 and 45,000 feet. Number three is a tropical easterly stream, so the opposite way to the first two, and this is a fairly weak jet stream at only 100 knots and an altitude of 50,000 feet, so we can pretty safely ignore this one. Number four is the polar jet stream between 60 and 65 degrees latitude, which also has speeds above 200 knots, but it's at about 75,000 feet, so we can ignore this one as well. So we're really only going to look at the first two. And I'm sure you've all seen this before. This is bobwins.com website. It's a copy of the earth.nullschool website, but apparently it didn't have or doesn't have the AE projection anymore. So some flurf copied the site and added it back in. So kudos on that. And I've added three circles on the map. In between the two white circles is this subtropical jet stream between latitudes 25 and 35. This is where the wind is supposedly up to 300 knots. In between the white circle and the black circle is the mid-latitude jet stream, which occasionally goes faster than 200 knots. And as we read in the citation, it has a wave-like meander. And this is the band of latitudes where QF27 spends most of the flight. So let's look at a few hypothetical scenarios and see if the jet streams can save flat Earth. Scenario number one is that we live on the AE map, but we're flying the Great Circle route, which is the green line going right around the perimeter of the map. So the cruising speed of the 7879 is about 488 knots, and we're going to assume a 200 knot tailwind, just like the citation says. Unfortunately, the distance is a whopping 21,000 nautical miles, and that would take you over 30 hours, while the average flight time of QF27 is a little over 12 hours. So that clearly doesn't work. Scenario two, we're going to stay in that monster jet stream between 25 and 35 degrees latitude that has a speed approaching 300 knots. So just to make things super easy, barely an inconvenience, we're going to calculate the AE distance by flying along the average latitude between Sydney and Santiago, which is that red line, 33.5 degrees south. Now I'm sure you flurfs can figure out the distance in your head, but for us idiot globers, we have to use a calculator and some math. And to do that, we have to figure out how far we are from the North Pole. So we add 90 degrees to the latitude, which gives us 123.5 degrees from the North Pole, and every degree of latitude is 60 nautical miles, so we are 7,410 miles from the North Pole. Now imagine we had to circumnavigate the dirt pizza. We'd multiply that radius by 2 pi, and we'd get 46,558 nautical miles as the circumference. But we're not going the full circumference. We're going from Sydney to Santiago, and they are 138 degrees of longitude apart, so not the full 360. So we scale it against that, and we end up with a distance of 17,847 nautical miles. Once again, we're going to give the flurfs the full 300 knots tailwind. But it would still take well over 22 hours to get there, when the average flight time in reality is 12 hours. So let's try the most obvious route. We're going to fly the AE route on the AE map, which is that yellow line. And I'm even going to be super generous and give you Muppets the full 300 knots of tailwind again. We're just going to ignore the fact that no one has ever reported flying over the USA on this flight. And calculate a flight time anyway. And once again, you just can't get there. 17 and a half hours against an average flight time of 12 hours. Right, let's look at those winds themselves. You'll notice that in all three of those scenarios, I applied the full 200 or 300 knots to the cruising speed. But if you remember back to the cited paper, it said they are occasionally above 200 knots and occasionally approaching 300 knots. And the data we looked at for the Bob Winds website and the earth.nullschool website come from the evil United States government, specifically the National Oceanic and Atmospheric Administration, NOAA. And over the last few months, I've downloaded quite a lot of wind data from NOAA, and I've written some code to look through the data and find the fastest wind recorded anywhere on Earth at a given pressure level. So the data you see on Bob Winds and Null School is at the 250 millibar level. And that equates to an altitude of about 34,000 feet. And if you remember back to the citation, the mid-latitudes jet stream that was occasionally above 200 knots was at a mean altitude of 35,000 feet. NOAA also provides data for the 200 millibar level, which is about 38,700 feet. So for the mid-latitude jet streams, we'll look at those two pressure levels, so 250 millibar and 200 millibar, in between latitudes 35 and 60. For the subtropical jet stream, which occasionally approached 300 knots, that was usually between 40 and 45,000 feet. So we can look at the 200 millibar and 150 millibar levels from NOAA, between latitudes 25 and 35. And obviously I've written some code to do all this for me, which will be in the GitHub link. So for the mid-latitudes, which is the 250 and 200 millibar levels, I only had 45 samples. Now the average top speed was only about 175 knots. And I have to be clear about what that number means. Basically for each data set, I'd find the highest speed anywhere between those latitudes, and then took the average of all of those top speeds. So the maximum speed I ever saw in those data sets was 208 knots, which is about 240 miles an hour. And I only saw 3 samples that were above 200 knots. So that's pretty consistent with what the citation said about occasionally being above 200 knots. So happy days. For the subtropical jet stream, I had more data at those pressure levels, so 62 data sets, but the results didn't really match the cited paper. The average top speed was actually lower than the mid-latitudes jet stream, and I had 0 samples over 200 knots, let alone occasionally approaching 300 knots. Just reading the paper, they clearly only did measurements in the Northern Hemisphere. So maybe we have to wait until the northern winter to see if they get anywhere near 300 knots. And maybe I was too late this year to catch any in the southern hemisphere. And then to round things off, we've got Jaren's argument, where he's not even trying to make it work on the AE map. He's saying there's something fishy with it even on the globe. Now I've asked him half a dozen times if we can schedule a live stream to go over all this, but it just never gets scheduled. So I guess this video is a substitute for that live stream. Anyway, let's have a listen.
And all right, so here's all the flights. They are Sydney to Santiago. What I'm going to explain to you is why we know for a fact that something's going wrong in the south. And Ruhif tried to come back and say, no, it's correct. And I said, okay, if you're correct, then look at these numbers. Okay, so look at the flight times. 12, 12, 12, 12, 12, 12, 12, 12, 11:53, 12:03. So let's take 12:01. Okay, so 12:01, the fastest flight in the last 15 or so. All right, so we know it's 7,100 miles. Let's go ahead and do some math here. 7,100 miles divided by 12 hours in the flight equals 591.66. Come on, iPad keeps closing. All right, 591 miles per hour. Okay, so that's what the plane is averaging. Now, if Mach 0.9 is how fast this plane goes, let's say, Mach speed at 30,000 feet, I think is like 700 miles per hour. Do we need to look that up? Mach at 35,000. Just to figure out what's the Mach speed. Mach is a ratio, for example, 35,000 feet, the cruising altitude of a typical passenger jet, the speed of sound is 660. Okay, let's just say we agree with that, even though that might not be true. We don't know, but let's just say it's true. So we're going now 660 times 0.9 for the Mach speed gives us 594. Okay, so that means that the plane is going about Mach 9 the whole way. But there's a problem. There is 150 plus mile per hour jet stream. My question again is why is this the only plane in the world not using the jet streams? If it is added 150 miles per hour plus 150 equals 744 miles per hour. If we take the 7100 by 744 divided by 744 with the jet stream, then we should see a flight of 9.5 hours. There's no flight in the history of all the flights from Sydney to Santiago that has ever gone 9.5 hours.
Right, so here is Jaron's inputs to his calculation. The distance between Sydney and Santiago, he says, is 7,100 miles. He says the plane's airspeed is Mach 0.9, which he equates to about 594 miles per hour. And he adds on 150 miles per hour for the jet stream. And he gets a predicted flight time of 9.5 hours, while the average time in the real world is a bit over 12 hours. So I realize Jaron's using a rough number here, but if you measure it on Google Earth, you get 7,061 miles or 6,135 nautical miles. No biggie, I just like accuracy. So second issue is that he's using an airspeed of Mach 0.9 when the cruise speed is Mach 0.85. So we'll assume a Mach speed of 660 miles per hour and therefore get a cruising speed of 561 miles per hour instead of Jaron's 594 miles per hour. When Jaron says Mach 0.9, he's probably referring to the maximum operating speed, which is basically the maximum speed that you can safely operate the aircraft. But could the aircraft actually be flying at Mach 0.9 instead of 0.85? Not really. This is an actual flight plan from flightaware.com, and most of these entries in the flight plan are waypoints. So looking at that second line there, it says go to 40 degrees south, 155 east, and do it at Mach 0.84 at 35,000 feet. So I don't really know what the excuse would be here. Either all the pilots are in on it and secretly flying at Mach 0.9 instead of 0.84, or maybe Boeing and Airbus are lying to the pilots and displaying a lower speed in the cockpit, or the planes are actually traveling at the airspeed that's in the flight plan. You'll also see that some of the waypoints have the speed in knots. So this one is saying fly to 43 degrees south, 87 degrees west at 488 knots and at 39,000 feet. Right, so the third issue with Jaron's explanation, and by far the biggest error. His flight time calculation assumes two things. One, that the jet stream is a constant 150 miles per hour. And secondly, that the direction of the jet stream is perfectly in line with the direction of travel. Neither of those assumptions are anywhere near true. Okay, so what I've done here is overlay a screenshot from the Knoll School website into Google Earth so you can see visually what jet streams the plane actually encounters on the route. So if you look at the first couple of hours of this flight between Sydney and New Zealand, you've got green lines, which are about 40 to 50 miles per hour. And if you look at the direction of those winds, you'll see that they are at about 45 degrees away from the direction that the plane is flying. So you're not getting the full 40 to 50 miles per hour as a tailwind. you're only getting about a 30 to 35 mile an hour tailwind. So if your airspeed is about 560 miles per hour, your ground speed is only about 590 miles per hour. But when you get to the southern tip of New Zealand, you start to encounter those purple winds, which are up around the 150 mile an hour mark, occasionally over 200 miles per hour. And again, they're a little bit offset from the direction that the plane is going. So a proportion of that speed is a crosswind and not a tailwind. But with all those varying winds, the big question is, how would you even go about working out the average tailwind to apply? Obviously, applying an average of 150 miles per hour isn't right, because like I said, it assumes there is a constant 150 mile an hour jet stream, and it assumes it's always in the direction of travel. Ta-da! So what I did was write some Python code that takes the tracking data from Flight Radar 24 and combines that with the wind data from NOAA to calculate a predicted flight time. So you'll see at this point A, we've got a wind speed of 101 miles per hour, but the direction of the wind is at 83 degrees azimuth, while the plane itself is traveling at 118 degrees. So we don't get that full 101 miles per hour as a tailwind. We do a little geometry and work out that we would be getting a tailwind of only 83 miles per hour. Then I add that 83 miles per hour to the plane's true airspeed, which in my code I've set to 559 miles per hour or 900 kilometers per hour. So adding those two things together, the ground speed of the plane at that point is 642 miles per hour. Then obviously I work out the distance between point A and point B to work out the time taken between those 2 points. Then do the same between point B and point C, calculate how long that little stretch takes, and so on until you arrive at Santiago. And then you just add up all those little time increments and boom, you've got a predicted flight time. So for this particular flight on the 16th of August, the actual flight time was 12 hours and 14 minutes, while my predicted flight time was 11 hours and 45 minutes. Now, for most of the flights that I've analyzed, the predicted flight time is usually about 10 to 15 minutes shorter than the actual flight time. And that's probably because my code assumes a constant airspeed of that 900 kilometers per hour cruising speed, which obviously isn't the case during takeoff and landing. And on this particular flight, you'll see that both the takeoff and landing were in the opposite directions to the direction of travel, which again requires more low-speed maneuvering, which I think explains the 30-minute difference between the prediction and the actual flight times. There are, of course, other discrepancies like slightly different winds at different elevations, different wind speed depending on the time of day, etc. But overall, I think it gives a really good estimate for the flight time, which is good evidence that both the track of the plane and the winds are correct. And if we do the same math that Jeren did, we can actually work out what the average tailwind over the entire route was, and it's only about 55 miles per hour. So like I said, you can't just assume that you've got 150 miles per hour right behind you for the entire trip, because that just isn't the case. And 55 miles per hour might sound pretty low, but if you have a look at the winds on the path, it actually makes a lot of sense. You've only got some small patches where you might be getting that 100 or even 150 mile an hour tailwind. The rest of the flight, you don't get much help at all. So that was a pretty long one, but hopefully it was pretty comprehensive. So thanks for sticking around. Just to sum everything up, what I've shown is that not only are these flights just impossible on a flat Earth, even with the jet streams, but I've also shown that the flight times, the ground tracks, and the winds are all consistent with the Earth being a globe. But honestly, this video really could have been 30 seconds long if I had posed a simple question to the flurfs. I mean, sure, let's assume you can get from Sydney to Santiago in 12 hours if you catch the Jetstreams. But how the fuck do you get back to Sydney heading into the wind?